Alright guys, so we're going to do a quick review of the heats of reaction material from the videos you should have watched. So there were a couple different things that we looked over in the video. One of them is if you were given a reaction with a heat of reaction, how to account for that. So here's the example given. And it talks about how much heat is transferred per mole of ammonia formed in the reaction shown below. So it gives us the full reaction and gives us the delta H value for the reaction as written. One thing to note that the delta H given is negative, so this is an exothermic reaction that is releasing heat. So within the question, it wants to know how much heat is transferred per mole of ammonia. So with 1 mole of ammonia. So that would be the start of our stoichiometry here. Now we're looking for heat, which is kilojoules. So we need to get rid of moles. And in our reaction that's given, we're getting rid of moles of ammonia. And we can change into kilojoules. Both of those are provided in the reaction. So it tells us that the negative 92.2 kilojoules is per 2 moles of ammonia in the reaction. So we would do the 1 mole times the negative 92.2 kilojoules divided by 2 moles of ammonia, and we get that it's negative 46.1 kilojoules. So you may see it written as a number. The other option is it may also say that the 46.1 kilojoules are released because it is an exothermic reaction which releases heat. So either way that you see this is appropriate. So let's look at this problem that deals with the same concept, where it wants to know how much heat is absorbed or released when 20 grams of ammonia reacts in the presence of excess oxygen to produce nitrogen monoxide and water according to the chemical equation. So here it gives us a different balanced equation, and it tells us our delta H of that equation, of that reaction, is positive 1,168 kilojoules. Notice because this is positive, it is going to be absorbing energy. This is an endothermic reaction. So looking at our actual question, it wants to know the heat or kilojoules absorbed or released when starting with 20 grams of ammonia. So we're going to start with the 20 grams of ammonia. We are ultimately looking for kilojoules, so we need to get rid of grams of ammonia. Grams of ammonia would need to go down to the bottom to change into moles of ammonia. So remember, grams is always out of 1 mole for molar mass, and molar mass of ammonia is 17.034 grams per mole. So that's going to give us moles of ammonia, but we're looking for heat or kilojoules. So we need to get rid of moles of ammonia. So in our next step, that would go down the bottom. And we have moles and kilojoules within our reaction. So that would be like our mole ratio step. So in our equation, it tells us we have 4 moles of ammonia per 1,168 kilojoules. That is going to leave us with kilojoules. So we're going to do the 20 divided by 17.034 times 1,168 divided by 4, and keeping it to 4 sig figs, that original number that was given, we get that this is 342.8 kilojoules. Now, pay attention to the question. It wants to know how much heat is absorbed or released. A lot of times, if it specifically says that, that needs to be part of your answer. So since this is a positive value, this many kilojoules are absorbed. So it's possible that if this was a multiple choice situation, you would have an option with the 342.8 kilojoules absorbed, and there would be an option with that same amount released. All right, so let's look at this one that is slightly different. But here it says at a constant pressure, the combustion of 5 grams of ethane releases 259 kilojoules of heat, and it wants to know what's the delta H for the reaction given below. So it gives us a reaction, and then it normally has like the delta H value off to the side. That's what we're trying to find, is the heat for this specific reaction based off of the data given. So we know that we are starting with the ethane, the 5 grams of ethane. Anytime we're dealing with like delta H, it is in terms of moles. So we would need to change grams into moles. So we can start with the 5 grams of ethane. Change into moles, so grams would need to go on the bottom to change into mole. So the molar mass for ethane is 30.068. See if I can fit it in this space. 0.068. There we go. So that is going to be 0.166 moles of ethane. And it tells us that much ethane releases 259 kilojoules of heat. So we can use that to find the delta H value for ethane. So for ethane specifically, if we do moles, or excuse me, kilojoules per mole, so the 259 kilojoules divided by mole, that means that delta H for ethane, for 1 mole of ethane, is going to be 1,560 kilojoules per mole. Now, looking at our balanced equation, there are 2 moles of ethane. So whenever we're looking at the reaction as a whole, we have to multiply this value by 2, because in our reaction there are 2 moles of ethane, not 1 mole of ethane. So that is going to give us a delta H for the reaction that is 3,120 kilojoules. And I left it at the original 3 sig figs that was in the 5 grams of ethane and the 259 kilojoules of heat. All right, so the ones that we looked at previously were all dealing with delta H of a specific reaction. There are other ways to find delta H values if they are not given, and we're going to go through each of these. One of the ways is looking for the heat of fusion for reaction. This will be using constant values that are either at the back of your textbook or they will be given for specific problems. There are also ones where we are using Hess's law, which we will review, and you will have a lab with this later on this unit. You can also find delta H by using the bond dissociation energy, which you may see abbreviated as BDE for short. That will look at the energy released from bonds being broken, or excuse me, the energy used from bonds being broken and the energy released when bonds are being formed. So looking at how much energy is released versus absorbed, and looking at the overall amount of energy in forming certain compounds. All right, so we're going to look at heat of fusion equations first. With these, you have the individual elements that are going to be combining to produce 1 mole of that product, of that compound, in the normal conditions. So you have to start off with elements on the reactant side. You have to end with 1 mole of product on the product side. And the elements should be in their normal state. So let's look at these equations and see if these would be appropriate equations to use for a heat of fusion reaction. So looking at the first equation, notice we have hydrogen, nitrogen, and O3 producing nitric acid. Well, we know that hydrogen, nitrogen, and oxygen are diatomic. So since these are not written as diatomics, this is not an appropriate heat of fusion reaction because you do not have the elements in their standard state. Looking at the second one, we have 2 hydrogens and 2 nitrogens and 3 oxygens producing 2 moles of nitric acid. We should only be producing 1 mole of nitric acid, 1 mole of product always. So this is not appropriate. So this is one of the cases where you might see fractions as your coefficients. Looking at the third one, we're starting with a compound and producing elements. These should only produce 1 product, and that product should be a compound. So if this was reversed, it might be appropriate, but not written as is. Let's look at the next one, the fourth one down. We have hydrogen, nitrogen, and O3, which is ozone, producing nitric acid. Oxygen is typically diatomic, not written as ozone, and this is not balanced. These should be balanced overall. So this is not an appropriate equation for heat of fusion. But looking at the next equation, the last one, says we have half a mole of hydrogen, which is diatomic, half a mole of nitrogen, which is diatomic, 3/2 of oxygen, which is diatomic, producing 1 mole of nitric acid. All of our elements are written in their standard states. Nitric acid, we're only producing 1 mole. And if you were to look, this is balanced overall. So that would be an appropriate heat of fusion equation. Typically, you're not going to have to write out these equations, but you may have to pick the appropriate equation out of a list. If you have to write out this equation, it's going to be something fairly simple and probably not this long. All right, so now that we've been able to figure out an appropriate equation for heat of fusion, how that gets used in more complicated equations. We do have in the back of our textbook, I believe it's Appendix 3, where there's a bunch of different tables. There are heat of fusion tables that give you the heat of fusion value in kilojoules per mole for every substance that there is. With heat of fusion, and I believe this equation is on your reference sheet, but the overall heat of fusion for a reaction is going to be the overall heat of the products minus the overall heat of the reactants. So you'll be able to tell if it's exothermic or endothermic, because if there's more heat of the products, it tends to release heat. If there's more heat in the reactants, it tends to absorb heat. So you'll be able to determine that. With these, you are going to be looking at the heat of fusion for the substance as written. One thing that you will notice is sometimes the state of matter does matter. So like there might be a different value for carbon dioxide gas versus carbon dioxide liquid. Same thing for water as a liquid versus ice. Pay attention to the form that you are looking for. There is also not a heat of fusion value for elements, because remember, heat of fusion, we are producing compounds. So there is not going to be a value for that oxygen that you're going to be able to find. And with these, you do have to account for those coefficients, because the heat of fusion values in the tables that are given are kilojoules per mole. So you have to account for if there are additional moles of that substance. So whenever we calculate this, we're going to have our products, which are the carbon dioxide, and there are 12 of those. Add that to our water, which there are 11 of. We're going to take that sum from our products and subtract the sum of our reactants, which here we only have the sucrose, because oxygen is going to be 0. So those are the specific values. We're going to have to look up the heat of fusion value for carbon dioxide as a gas, water as a liquid, and sucrose. So I attached a table down below. So let me see if it will let me. It doesn't let me scroll very nicely, but we will make it work. So carbon dioxide as a gas has a heat of fusion value of 393.5 kilojoules per mole. So if we put that into our original equation, we're going to have 12 times the 393.5. And remember, that is kilojoules per mole. So your moles end up canceling out, leaving us with kilojoules. We need to do the same thing for water. These are alphabetical, so water is going to be at the end. And remember, we want water as a liquid, not water vapor. It tells us the delta H for water as a liquid is negative 285.8. And remember, there are 11 of them, so that was negative 285.8. And that's all of our products. That is going to subtract our sucrose, and there's only 1 mole of sucrose. And sucrose has a delta H value of negative 2,221. So be careful of these when you put them in the calculator, because you have to have those brackets or parentheses in the right locations. Another thing you can do is get the total for the products, the total for the reactants, and then subtract them. If not, it will give you a funky answer. So whenever you put this in, ultimately, you are going to get that it is negative 5,644.8 kilojoules. Now here we're not given any original values to start with, So we do not have to worry about sig figs in this case. You don't have to worry about rounding or changing it. So this is our final answer. So this overall reaction should release 5,644.8 kilojoules per mole of the reaction. All right, so let's look at this example. And this is a problem dealing with Hess's law. So with Hess's law, it reminds me of kinetics whenever we did mechanisms, where you had smaller reactions that added up to equal the larger reaction. So here it wants the heat of reaction for 2 moles of magnesium and a silicon tetrachloride producing silicon and 2 moles of magnesium chloride. And it gives us the smaller reactions of the heat of fusion with silicon and 2 chlorines producing that silicon tetrachloride and its heat of reaction that corresponds. It also gives us the reaction of magnesium and chlorine producing magnesium chloride and its corresponding heat of reaction. So in order to find the heat of reaction of the overall equation, we have to figure out how to use these smaller equations to make up the larger equation. So we need to decide, do we need to flip the equation? Do we need to multiply by a number and cancel out some of those intermediates and things that are on both sides of the equation? So here, notice the first equation with silicon, chlorine, and silicon tetrachloride. Silicon tetrachloride is a product here, but in our equation, it is a reactant. So we need to flip this equation, and I will just rewrite it flipped because sometimes that helps us in the long run. And what we do when we flip the equation is that now changes the sign of the delta H. So our original equation was exothermic. It was a negative 687 kilojoules. When we flip the equation, it is now endothermic. So we just change the sign from negative to positive. And if it was originally positive, it would now be negative. So that gets rid of this first equation. And you can always check your number of moles. Like there's 1 mole of silicon tetrachloride, 1 mole of silicon tetrachloride. So we don't need to change our coefficients at all here. Well, looking at the second equation, we have 1 mole of magnesium, but in our overall equation, we have 2 moles of magnesium. So we need to double this bottom equation. So that would be 2 magnesiums, 2 chlorides, 2 magnesium chlorides. And what that does to our delta H value is we also multiply by that same coefficient and double that as well. When we add these together, that's going to allow the 2 chlorines on both sides to cancel. And then we're left with, on our reactant sides, the 2 magnesiums, the silicon tetrachloride, the silicon solid, and the 2 magnesium chloride. So since we were able to add together those equations to get our original equation, we take our delta H values and add them together. So we add the 687 plus 2 times the negative 641 kilojoules. So make sure that you have changed the sign or multiplied those numbers. And this gives us an overall delta H value of negative 595 kilojoules. The meeting is about to end, so I will stop the first video here and pick up with part 2. We have 4 more examples to go through.